Today we're going to just do our introduction to electricity. Okay, so let's say we have a 1.5 volt battery, right? And it's so basically what the point is that electrons they go to negative to positive, like in the real life. Like it goes through the light bulb, and it heats up the generator that, and then it creates light, and it goes like this. However, when we're going to study, we're going to talk about current going like to the different, like positive to negative. So just know that. So the battery is singled like this, and we have a resistor. I mean, we should already know this because I did a few videos about this. However, beside the point, so let's say, so this is the battery, positive and negative. Let's say we also have 6 volt. It's like 6 volt. The battery is 6 volt. The resistor is 50 ohms, and the current. Again, I'm just going through the basics. So Ohm's law, IR. So we need to find out the current. What's the current? Well, we're able just to make it the formula as if like, so 50 divided by 6, which is let's just put, wait, oh no, sorry, that was wrong. So the voltage first, then the resistance. Don't make my mistakes. So 0.12 amps, and then we're also able to find out the charge if we need to. So charge, which is into Q, Q equals IT, and there are other like formulas, so this is the main one. So Q equals charge, like the electric charge, and it's measured in coulombs, and then a current, which is measured in amps, and then time is in seconds. And so from this formula we know that 1 coulomb, so 1 coulomb equals 1 amp times 1 second. However, we're also able to, like, if we don't have the voltage, for example, we're also able to say that, like, we're able to arrange formulas, guys. So I equals charge divided by the time. So we're able to do all this type of stuff. So let's say we need to increase voltage. The way we do that is that we're able to put batteries in a series. So let's say both of them are 1.5. So if you were to measure them, the voltage of what's happening here, it will show you 3. However, if you want to increase the current, so we're able to do something different. So we're able to put the batteries in parallel, and the reason for that is, so let's say this battery is 10 volts. Oh no, not 10. Let's say this battery, when it goes on, it gives out current of 10 amps, and then when this one is on, it gives current of 5 amps. When these combine, they give 15 amps. And also, when they're in parallel, the current doesn't add up like this one because they're in parallel. Series, it works like that. Over here, it doesn't. So just know the difference. So let's just quickly understand what voltage actually is. So basically, voltage is the potential difference between two points. So let's say we have A and we have B. This is a resistor. A, the voltage is 30 volts. So like this is the positive side, this is the negative. Over here, it's still a positive, by the way. So they're both positive numbers. And over here it's 10 volts, and the resistor is 5 ohms. And as we know, current goes down and electrons go up by the way, because they're negatively charged, so they go negative to positive, and it's the opposite for current. But that's basically what I'm trying to say is that the voltage would equal to VA take away VB, which would be 30 take away 10, which equals 20 volts. So the resistor has 20 volts, like when it's over here there's 20 volts basically. And after that we're able to find out the current, which is like the current in the resistor, because like, you know, it's different, like there can be current here. Basically it's about where it is. Of course current can't be like randomly in the middle, however, I mean it can, because like we're talking about the whole of it, but we're talking about exactly when it passes the resistor, what is the current there. So 20 divided by 5, because that's the voltage, divided by the resistor, which is equal to 4 amps. And then after that we're also able to find like out that what is the work done, for example, because work done is the charge times by the voltage like difference, but that doesn't matter. Okay, here is our first example. So a 12 volt battery is connected across a 4 ohm resistor. So let's just draw that. So we have a 12 volt battery and it's connected to a 4 ohm resistor. What is the current flowing through the resistor? So we have to know the current, which is I equals VR, so 12 divided by 4, which is equals to 3. So the current is 3 amps. After that, how much power is dissipated by the resistor and how much power is connected, delivering by the battery. So look, there are three ways of calculating the power. However, over here we need only 2. So first of all, let's talk about how much power is in the resistor, like how much is dissipated by the resistor. For the resistor, we're going to use, I'm pretty sure it's I squared. Yes. Power, which is measured in watts. I think I should do something more readable, something like this. And then, so 3 squared times 4. Now, can we do it? Okay, 3 times 2 times, so 9 times 4, which is going to be 36 watts. So over here there's 36 watts over here. And now the second part is and how much power is delivered by the battery. So now we have to use the formula where there is a voltage, because like guys, you have to understand that power, it's basically energy divided by time. However, that's beside the point. Let's just do the calculations. So power, and then 12 times 3, so V times I. And because this time we're using voltage, because it's talking about the voltage, even though it's going to give the same answer, but it doesn't really matter. It's just so we understand that there's a difference. So yeah, that's how it is with the power. How much electric charge will flow in this circuit for 1 minute? So the electric charge is kind of, no, it's not different, but so let me just quickly get rid of this because we've got the answers already. So basically power, not power, charge is equal to the current times the time. So that would be 3 times 60. So that would just be 180 coulombs. After that, how much energy is consumed by the resistor in 1 minute? So basically, power and energy, they're different. And so power is measured in watts and energy is in joules, even though they're kind of similar, but not. So even though we know that, so let's say 36 watts are equal to 36 joules. It, basically, yeah, just know that they're similar and equal, because there can't be more or less if there's the same. So there can't be more or less of 36, basically, because watts are like directly kind of connected to energy. So 36 joules per second, like let's just put second, like every single second, and then we times it by 60 because that's how much in 1 minute. So 336 times 60 is equal to 2060 joules, because joules are in energy. So yeah, that's the answer for this one. And then how much work is done by the battery in 1 minute? So we know that work done is equal to the Q. So basically what this question is asking is how much can a 12-volt battery, how much work can it do when there's 180 coulombs and 2000 and 1060. So how much joules can flow while there's 160 joules going through that battery? So, however, because we're dealing with like how much work is done, and work, when we calculate work done, it's in electrons, and electrons are negative, so we do the negative Q. So what basically it is, it's negative, no, it's 180, but we put a negative, and then we times it by 12, which gives us 2160 joules. However, we also would be able to do work power times time. It gives the same exact thing, but that's a different formula which doesn't really work. As if no, it does work. It gives, but that's not right. We have to understand actually the theory. So we talked about like the voltage. We talked about the current. We talked about the resistor, but not that much. So we know that this is the sign of like resistor. However, there's also conductance that is basically different to resistance, but like in a way as if like they're connected to, but in a different way, like they're similar but differently. So conductance is shown in a G, and it is equal to 1 over resistance. And so like resistance is measured in ohms, and the conductance measured in Siemens, something like that. So let's say there's the resistor 1 ohm, and the conductance is 1 Siemens. Let's say there's 10 ohms of a resistor, but that then there will be 0.1 Siemens conductance, like yeah. And then let's say there's 0.1 resistance, then the Siemens will be 10. So like when the resistance goes up, Siemens go down, and when Siemens go up, resistance go down. So resistance is equal to the pressure, or pressure, length divided by the area. So pressure times length divided by the area. So let's say we have two wires. Like they should have the same diameter. Whoa. So let's just make it this way. So let's say this one had basically resistance is like the length is an option there, and the area is also. However, you have to understand that if the long one will have more resistance. The reason for that is that like the longer the length, the more resistance, because there's more to go through. I kind of explained this in a different video. I can't remember what video, but I am sure I already explained this. So yeah, if you want to understand this even better, go check the other video. But like, still watch all of my videos, guys. So with lengths, you have to know. So let's say, for one, what's it called? The wire, there's 2 ohms of resistance each 500 meters. So for 1000 meters of the same wire, the resistance will be like 4 ohms. Same with like feet, like you can have it like this. So just know that this is how kind of you write it, right? Now let's say you have 2 wires which are the same length, but the area, like the diameter area, are different. So let's say that A and B, A is more thick. So where do you think this time is going to be more resistance? Well, the answer is A. A will, well, it won't have more, it will have less. Basically, if you increase the area, the resistance will decrease because there's more space for the electrons to go through, right? And over here they're like fudged up, so it's more harder for them. So understand that length increase resistance, area decrease increase resistance. Basically, yeah, these are what you have to understand. So I also made a mistake. So I said that this is pressure. It's not pressure, this is resistivity. Basically, resistivity. Each material has its own resistivity. So let's say Ag, which is for silver, and Cu for copper. The resistivity is different from, it is basically, just go check the other video out. The resistivity for silver is 1.59 times 10 to the power of minus 8. For copper, it is 1.68 times 10 to the power of minus 8. So this one has more resistance because it has a larger resistivity, so it's just logical, larger number, which means larger resistivity. So like the resistivity, so let's say we have, so metals, for example, they are conductors. Conductors are the ones that like we use to like for electricity, for wires, blah blah blah, because the resistivity is very low. So if the resistivity is very low, the resistance is low, because so it's 10 to the power of minus 8, which is low, like the number and the power, I guess. And then we have semiconductors that are like metalloids. I'm not really sure what that is exactly, but they also have a pretty low resistivity, which is, it usually is times by 10 to the power of minus 3. And then insulators are the ones that we use to insulate from electricity. They have a very, very, very high resistivity. For example, it's like 10 to the power of 9, 10 to the power 2 to the power, no, not minus. So basically this. So yeah. Also, if like the temperature of the metal goes up, the resistivity goes up, therefore resistance goes up. And there's also this one formula that's like P0 1 plus with this sign, which is basically it shows what the metal is like. It's basically what it shows. I don't know, it's basically, I know what that they give you an exam. And then this the formula.